Hey everyone, Geek37 back with another video. And this is an extension of my last video which established the basic trigonometric ratios sine and cosine in both the regular heptagon and the heptagonal triangle. And since the heptagonal triangle is just a subpart of the regular heptagon, I had to use that to derive the identities. What I'm going to do is I'm going to focus on the cosine ratios that I derived in the last video. And what we're going to do is we're going to do a couple of calculations that appear in mathematical olympiads. And I honestly think this might be the simpler way to solve those problems instead of having to do a bunch of trigonometric manipulation to get to the answer. I don't know how many people would agree with that, but let's go with it anyway. Now, as you can see on the right, we have the heptagonal triangle established, so you know where those angles come from. I'm not going to show the derivation of these cosine angles because I want to save time, unlike that last video, which took a long time to go over. So from the last video, we showed that the cosine of pi over 7 was b over 2a. We showed that the cosine of 2 pi over 7 was c over 2b. And we showed that the cosine of 4 pi over 7 was negative a over 2c. So those are the three main trigonometric ratios associated with the heptagonal triangle. But down below, you'll notice the cosine of 3 pi over 7. That is actually more established with the regular heptagon, but I am here showing it because, like I said, I've seen this ratio show up in mathematical Olympiad problems. So what we're going to do is we know for a fact that the cosine of 3 pi over 7 is supplementary with 4 pi over 7. And since the cosines of supplementary angles have a negative version of it because of the identity for that, we already have the obtuse version, 4 pi over 7, having negative a over 2c. So since 3 pi over 7 is acute, it's going to take the positive version a over 2c. So here's the calculation that I want to go over. We're going to take the cosine of pi over 7 times the cosine of 2 pi over 7 times the cosine of 4 pi over 7, and we'll see what that works out to be. But since we have the ratios already established from before, we can show, just by doing some simple algebra, that the solution is pretty easy. So we cancel off the b's, the a's, and the c's. The numerators are basically empty, so those become 1s, and we have a negative 1 on the end here. So we take 1 times negative 1, which is negative 1. And on the bottom, we're left with 2's. 2 times 2 times 2 is 8. So the product of cosine pi over 7, cosine of 2 pi over 7, and cosine of 4 pi over 7 equals negative 1/8. I've always thought that was a fascinating answer to these three weird cosines where Americans typically don't deal with pi over 7 unless it's in a mathematical Olympiad, and it comes out with this nice, neat answer of negative 1/8. But the thing is, we also have that cosine of 3 pi over 7. So let's do that product next with pi over 7 and 2 pi over 7. Like I said, I've seen this before in videos that do these mathematical Olympiad problems. So again, we set up the ratios below here, b over 2a, c over 2b, times a over 2c. We cancel the c's, the b's, and the a's. All the numerators are left with 1. So we multiply them, we get 1. Multiply the denominators, we get 8. So the final calculation for cosine pi over 7, cosine of 2 pi over 7, and cosine of 3 pi over 7 is equal to 1/8. Now, bear with me as I rant here for a bit. I think students who are given these calculations, especially with odd denominators like 7 or 9 or 11, instead of doing all this massive trigonometric manipulation, which can be quite difficult, if students are taught that the denominators of these radian angles, of these trig ratios, can associate to a regular polygon, they could be able to learn how to manipulate those, and they can come up with these ratios pretty quickly, and then they can finish the calculation in probably about the same amount of time. But I don't see that being taught, and I think that's an avenue that should be more explored in future contests if these problems are given to students. But that's just my opinion. Maybe you agree with me, maybe you don't. But I will say this: I hope you enjoyed this video. I enjoyed making it. This is Geek37 signing off.